So number 3, what is the volume of the air in a balloon that occupies 0.620 liters at 25 degrees Celsius if the temperature is lowered to 0.00 degrees Celsius at constant pressure? So we have a trapped body of gas. That trapped body of gas is undergoing a changing set of conditions. And so the formula that I would jump to consider would be P1 V1 over T1 equals P2 V2 over T2, the combined gas law. Now, since it says that the pressure is constant, that means I do not have to concern myself with pressure. So I am going to go ahead and eliminate that from the problem, because it is not going to influence the other variables. All right, so then it says that the initial volume, V1, is 0.620 liters at a temperature of 25.0 degrees Celsius, that V2 is unknown, and T2 is 0.00 degrees Celsius. In this equation, so if I put in liters, I'm going to get liters out. So V2 is going to come out in liters. 3 sig figs, 3 sig figs, 3 sig figs. So my answer will be 3 significant figures, whatever it might be. Temperature is decreasing. So since the temperature is decreasing, that makes me think, so that means the particles are going to be moving more slowly. If they're moving more slowly, then it's going to be difficult for them to work against the elastic containment of the balloon. So I think that the volume should decrease in some way. If you listened at all to what I have to say, you know that we cannot use temperature in degrees Celsius, because the temperature measurement that we need, like, right, this volume would have to come out to be 0 if you'd have any mathematical sensibilities. So we have to use the temperature scale that relates to the molecular motion, which is the Kelvin temperature scale. So we need to convert 25 degrees Celsius to Kelvin by adding 273. That means it's 298 Kelvin. Temperature of 0 is just going to, so you add 273, it equals 273, tough math. And so we're going to solve for V2. It's probably easier for you guys to plug in the numbers, and then, like, so the way you guys were taught to do algebra, you should cross multiply, and so you end up with V2 T1 equals V1 T2, and then when you want to isolate V2, you divide T1 over to that side. So V2 is going to equal V1 times T2 over T1, and so that's going to equal 0.620 times 273 divided by 298, and so V2 comes out to be 0.56798. Now earlier we said we were going to round it to 3 sig figs, so let's call it 0.568 liters. All right, so that's our answer to number 3. Let's try, we're going to squeeze number 4 in here because I don't feel like erasing this board again. And this is the last problem. This is officially the last problem of the night. So. All right, so number 4. A gas in a sealed and rigid container has a pressure of 125 kPa at 30 degrees Celsius. If the pressure in the container is increased to 201 kPa, what is the new temperature and pressure temperature in degrees. And then since it is a sealed and rigid container, that means here in number 4, volume is constant. And since volume is constant and we have a trapped gas undergoing a changing set of conditions, I'm not even going to put volume in the equation in the first place. And so it's going to be P1 over T1 equals P2 over T2. Looks like P1 is 125 kPa, T1 is 30.0 degrees Celsius, and you're going to have to convert that to Kelvin, so that's going to be 303 Kelvin. P2, I think, is what we're solving for. Nope, P2 it gives us. It's 201 kPa, and T2 is what we are solving for. Oh, and it asks it for it in degrees Celsius. So when we solve for it, it's going to come out in Kelvin, and then we'll have to subtract 273 to get it in degrees Celsius. That's a little bit tricky. All right, so since the pressure, both are in kPa, that's cool. 3 sig figs, 3 sig figs, 3 sig figs. So when we get to the end, we subtract 273. Maybe it's, so the subtraction kind of throws off sig figs. We'll round to 3 here, and then the subtraction, we'll see what happens. Let the chips fall where they may. Since the pressure is rising, the temperature is going to have to rise, right? If the volume isn't changing, then the particles must be moving faster and hitting the walls of the container more often. So then we want to solve this for T2. So you cross multiply and then divide. So you end up with P2 times T1 over P1 equals T2. And remember, if T2 doesn't come out to be bigger than that 303, then we did something wrong mathematically. So we're going to take we're going to take 201 times 303 divided by 125, and T2 should come out to be 487.2, so we said 3 sig figs, so 487, but that's Kelvin. If we want to put it back in degrees Celsius, we got to subtract 273, and so I get the temperature to be 214 degrees Celsius. So that is this temperature down here. The final answer, T2, is 214 degrees Celsius. All right, that's the lecture examples for Unit 9.